In this video, we get into the register bus integration, and I go into a long overdue block diagram showing what my target computer is supposed to look like. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. Well, I have my build out now, and the purpose today is to handle the register and make sure that it's configured to handle all of the outputs to the different buses that we're going to need. So while I'm performing this, I'm going to actually disconnect the clock module and set it aside because honestly it's going to be a little bit in the way and I'm not going to be able to get everything into the picture. Same thing with the test harness. I'm going to disconnect that and set that out of the way so that I've now got my base register here. Now, in the interest of full disclosure here, I have tested to make sure that everything I want to do will fit on to 3 additional breadboards. So I did do some pre-work here off camera. And so I'm bringing in 1, 2, 3 additional breadboards here. And I have 4 line drivers, 74 LS541s. That I'm going to use to drive the contents of the register out onto the various buses that we're going to need. So let me get this hooked up here real quick. And this is going to be a rather large rather large breadboard stack here. And then I'm going to set these 541s in place. And I'll get into a little bit about what each output is going to be because I figure this is going to be a rather long wire up, and long overdue is a discussion or a description of exactly what the computer design is going to be. I'm checking the pins here because it doesn't seem to be wanting to drop in very easily. So there we go. Nope. Did that work? It did not. I have to roll the pins, that's why it wasn't. So long overdue is that conversation about exactly what the design of this computer I'm building actually looks like. And so I figure since this is a long wire up today, I might get into that and provide that description so that everybody understands what the different buses are going to be and how we're going to go about tackling those. I need to roll this one a little bit too. And all I'm doing is putting it on a flat surface and very carefully, because you can actually overdo it, rolling the pins such that you can see they're splayed out just a little bit, and I'm rolling them such that they point more straight down, which is more conducive to getting them into the breadboard. So you can see the after there. It's more of a straight down direction, which makes it easier to drop in. And so, again, being a long wire up, I figured I'd take some time, and while I'm doing the wire up, and you can watch that on one part of the screen, I do a description of what I'm doing, what the end goal state is on another part of the screen. That might have rolled a little bit too far. No, I think I'll be all right with that. All right, so those are in. Again, these are 8-bit line drivers. So for my register, I need a pair of those. Pin 1 and pin 19 are the enable signals, yes. And they are active low. So whatever I do to the most significant byte, I want to do the same thing with the least significant byte. So I will tie pin 1s together for each pair and pin 19 together for each pair. this being a pair, this being a pair, and then 2 more pair, and then 2 more pair as we move up the breadboard. Power and ground and decoupling capacitors. And again, my thoughts on decoupling capacitors on breadboards, I'll link up there. And then with that, the whole purpose of me laying this out ahead of time is I actually need to extend the output here of the register. The register itself is down here. I need to extend this output up this side of the board, and I need 16 rows to be able to do this. And this 16th column here gives me enough room to lay out 16 bits of data going all the way up the side of this breadboard. And then I can extend it over into this set of line driver inputs and this set of line driver inputs, where the outputs are going to be up here. Again, extending over into these inputs where the outputs are going to be up here, and extending over into these inputs where the outputs are going to be up here. Now this is going to be quite a long wire up. I honestly am probably not going to be able to do this all in one sitting in real time, so you may see some cuts to different board positions as I have to step away and come back. But the first order of business is going to be power, ground, and tie the control lines together here. And then once I have that taken care of, extending these up the side of the board here, and then tying them in over here. And while I'm doing this, I will, in a separate screen, describe what I am going for with this computer. As I've said before, this is a big wire up. I've divided it into 5 concurrent videos to the right of the screen. There's 144 wires just to distribute the data to the ICs. That doesn't include power control, the decoupling capacitors, or any of that. So it does take a little bit of time, and I tried to divide that up accordingly so you didn't have to watch the same thing 6 times. The clock module has already been built. It is an early iteration of that. As we get deeper into the build, we're probably going to need some additional functionality added to it, and that may spark a redo of that particular module. But until we get there, this will suffice for the time being. All registers are going to be 16 bits. We've already started building that out as well. The program counter needs to be able to increment. The stack needs to be able to both increment and decrement. And I'd like to have all the registers have the same functionality. It makes it easier for ordering, because you've got to order multiple PCBs at once. And if I end up having the same PCBs for all the different registers, there's economies of scale there. So I'm planning on all the registers having the same functionality. Whether all that functionality is used or not will be a different story. The current plan is to have up to 32 different registers. Now that seems ridiculously large in a 16-bit machine. But because of the way I'm going to handle some of the memory, additional registers will be handy. Plus I'm planning on doing an interrupt, which I'll get to in a minute. Having 32 registers will allow me to do some register renaming. Now, the bus, singular, the bus is the most contested resource in the computer. And so to get around that, it is nice to be able to divide things up into separate buses related to the function that they're going to provide. And that is actually what I want to get into today, because a lot of what I'm doing on the register wire up, as you see to the right, is related to the number of buses that I'm going to have. Now, outlined here on the left is an address bus in purple, the purple dotted line, and then there's a blue dotted line that goes from memory to the 16-bit instruction pipeline. The program counter is obviously going to contain a memory address. And this is going to be asserted on the address bus 1, which is going to be the fetch bus, the instruction fetch bus, I should say. And the address is going to contain, memory is going to contain a 16-bit instruction for the pipeline. So you're going to retrieve a 16-bit instruction and stuff it into the pipeline. Now, all memory access is going to be 16 bits wide, meaning that there's not going to be byte level access. That's how I'm going to be able to get to 128K of memory in a 16-bit address. Is bit 0 is always going to be assumed to be 0. Everything is access word aligned, 16-bit aligned. So that gives me a bus count of 1, the fetch bus, the instruction fetch bus. There will be a second bus for memory access, normal memory access. And those reads in memory will be able to happen in parallel with the instruction fetch. To do that, I'm going to have some shadow memory implementation. Writes, on the other hand, will inhibit the fetch. And so when a write is performed to memory, it is going to have to stall the fetch unit in the pipeline. The main bus will be allowed to move data from register to register. And there's a special operation on the main bus that we want to be able to support in case we need access to just the high order byte of any particular 16-bit word. And that's going to be a byte swap. So a special form of the main bus is going to be generated that does a byte swap, swapping the most significant and least significant bytes, still keeping the same bit order within the bytes, but swapping those 2 bytes so that you can have access to the high order byte if you need to do byte operations for any reason. And that now increases our bus count to 4. So I've got address bus 1, address bus 2, the main bus, and a byte swapped version of that main bus. There will also be 2 ALU buses, one for the left or A side, one for the right or B side, and those are going to come from the registers themselves. And that completes our bus count. There will be 6 buses. To complete the computer design, I am going to build an interrupt controller from the get-go. I want to be able to support interrupts, not have to pull for every single bit of data, every single activity that needs to happen on the computer. I'd rather have hardware level interrupts associated with that. I'm also planning on some special I/O registers for interacting with hardware. The plan is for 32 I/O registers right now, and that will support 16 devices. The plan is to have 1 control word that can be written to or read from to get status, and 1 data word for reading and writing data for each. So 2 registers, each can read and write for each device, 16 devices, 32 I/O registers. The peripherals I'm planning at this point to add to the computer are a UART. I do want to provide video in the form of text, not graphics. A keyboard. I do want some kind of a timer or counter that can interrupt the CPU. And then some sort of storage. Not sure what that's going to be at this point, but I do want to be able to support some kind of storage. Now, any 8-bit peripheral that is hooked up to my 16-bit computer, where everything is operated on as 16 bits, the most significant byte will be ignored or dropped. So on a read, the most significant byte will come in as zeros. On a write, the most significant bits, 8 most significant bits or the most significant byte on the write will be just dropped and ignored. Okay, here it is, almost completely wired up. I'm going to take and elevate the back of this to try to combat some of the glare here. See if it can improve. I have to relocate my light above because it's shining straight down and then back up into the camera. So once again, here we've got our registers, and underneath here we've got 2 line drivers which are used to drive the LED output. As part of the input to those line drivers, I am capturing what's coming off the register here. So here's the register output here. I'm capturing that and taking it up the side of the board here. And then on each of the boards, each of the individual breadboards, I'm extending the signal over so that I can drive each pair of line drivers. Now, up here we'll have address bus 1, and this one's going to drive the fetch register, or the fetch cycle for the pipeline. Address bus 2, this one is going to drive memory access for reads and writes to memory. I've got the ALU A here and ALU B. These are going to be inputs into the ALU to keep them off the main bus to try to reduce some of that contention. And then down here, both of these are the main bus. This is going to be the main bus in natural byte order, with the most significant byte and the least significant byte. And then over here, I am going to have the output to the main bus by inverting these. So this is going to be the least significant byte and the most significant byte. It's going to swap those bytes. Now, I do want to tie these together because I don't want to have 2 connections to the main bus. So it's really easy to tie these together. But the main bus is also going to end up coming down here and being the input into the registers. Before I tie those together, there's one more breadboard that will end up being included down here for some of the increment and decrement functionality I talked about in the computer design. So I will be adding one final breadboard here, and then wiring at this point the main bus all the way down as the input into the bottom breadboard. I'll get to that in a future video. What I do want to do is wire this up so that I have only a single main bus connection here. And doesn't matter which of these 2 are asserted, the main bus will be picked up. One more thought here. I did add a yellow color to the breadboard, and that's going to be for control lines. And then at the same time, I'm going to wire up some LEDs for testing, because I do need, that's huge wire up here, I do need to actually make sure that it's working the way I want. For the testing purposes, there's 2 control lines for each of these line drivers. They are tied together. Each pair is tied together. And I believe, for testing, I'm going to take and tie the pin 1 to pin 19 so that I can easily control enable without having to move 2 wires. I'll just need to be able to move 1 in order to enable one of these outputs for testing. And then I've got a couple of ribbon cables I need to wire up as well to facilitate that test. So I will get going on making all of those changes, and we'll see you on the other side of that for some testing. As I get close to the end of the register module build out, I've got 2 or 3, I think, more videos to do on this. And then I need to move it all into KiCad and order PCBs for this. If you have any interest in seeing how this gets laid out in KiCad, leave me a comment. I'm not sure I want to record all of that and voiceover or explain what I'm doing as I'm doing it, because it can be kind of difficult to follow. I don't get motion sickness, but watching others that have done this, I find myself just not able to actually watch the screen because it gets to be just, things move too fast. So if you're interested in that, let me know. If you've got any ideas on how I could produce or edit that so that it would be a little easier to follow, let me know, and I'll definitely do it if people want to see that. Yeah, I managed to drop one of the wires on the board, promptly lost it, and then cut an extra wire, so I'll save that for a rainy day. These are all wired up, and I've got the least significant byte here wired up to the most significant byte there, and the most significant byte here wired up to the least significant byte. If I pick up my bus connections here, that is inserting onto this bus will carry it over here, and I will be able to pick them up in reverse byte order. I can do that because I do not plan to ever assert the main bus and the byte swapped main bus at the same time. And when one of these line drivers is not asserted, it is actually a high impedance, as if it's basically disconnected from the bus. So that allows me to do this without actually worrying about harming the chips. If you saw my video about the inverter that I harmed, that does not have the high impedance disconnect that these line drivers do. So that's the difference that allows me to be able to do that. And once again, I'll extend this down further. Now let me get that wire harness. For the register output, I'm using, again, these LED graphs. I'm using 8 of the 10. I will use green just to indicate the data. The yellow and the red will not be used. And it's real simple to drop those into the breadboard, add a couple of 220 ohm resistors, one for each LED that I'm going to use, and then get that tested so that I can confirm that I've got everything wired up the correct direction. Then I need to get into making a ribbon cable, and I've gone through this and it's fussy, and if you want to see how I make the ribbon cables, I will link to the video in the upper right hand corner on one of the cards. In the meantime, I will go ahead and just cut this short and move on to the rest of the build. Okay, well, let's bring the build back in and hook up my test harness. I also bring in the output, the clock, and try to hook it up, and nothing would work. I did finally get that sorted out, but it comes back to haunt me again later. I never really identify the root cause at this stage. Not sure what was going on there. Now, I did mention that I was going to tie pin 1 and pin 19 together, and then take the whole thing to high for now. Again, this is another situation of second first, same as the first, so I'll fast forward through this as well. Okay, so now I'm on address bus 1. Here is my value that is on the register at the moment. And if I switch this to be low, I should see that out here, and I don't. Well, I'm very aware of the length of this video at this point. I did capture all of my troubleshooting video, but it just makes this particular video way too long if I was to include it here. So what I'm going to do is I'm going to stop this here and unfortunately leave you on a cliffhanger, and then I will turn around and start working on the next video, which will be dedicated to the troubleshooting of this and getting that cleaned up. I do have it cleaned up. It is working properly, but I want to be able to demonstrate the troubleshooting because I think that is an important piece of the build process. So stay tuned.